We're going to talk about an exciting topic. We're going to talk about the business impact of code quality. And we're going to cover a lot of ground today. So I like to approach this topic from the perspective of technical debt. So what I find interesting is that we, as an industry or as an organization, we take on technical debt for multiple reasons. The most common reason that we're probably all familiar with, that is when, we have this feature, we would like to get it out really, really quickly. So we try to cut some corners, we compromise quality and hope we can deliver it quicker. Ever seen that happen? Yeah, all the time, right? So that's like the classic. But there's also the other side of it where we actually do the right thing. We have a proper design that works really well, but then at some point our understanding of the problem we're trying to solve changes, which means that our original design might no longer be a good fit, right? And then maybe a highly hypothetical scenario is that perhaps, just perhaps, our design wasn't a good fit to start with, right? No matter the root cause, we end up in the same situation. We end up with code that is more expensive to maintain than it should be. And this is the definition of technical debt that I'm going to run with throughout this presentation. And what I find fascinating is that we actually know a lot of things about technical debt already. Because of the past years, there has been some pretty exciting research that has managed to quantify the cost of technical debt. And if you read the various papers, they all come up with different numbers. But at the end, it doesn't really matter, because what they all have in common is that they are a pretty depressing read. It turns out that we, as an industry, we waste roughly 23 to 42% of developers' time dealing with the consequences of technical debt and bad code in general. 42% waste. What does that actually mean, right? I don't have a financial background, right? So let's try to do a thought experiment to wrap our head around this. So let's say that we have a company and we have 100 engineers. With a 42% waste, it would mean I pay the salaries for 100 people, but I get the output equivalent to just 58 people. Does that sound like a good deal to you? No, it's horrible. It's a horrible waste. But the thing is that if you could do the same system with just 58 people as opposed to 100, that would always be the more efficient option, because with 100 people, you have the additional management overhead, coordination overhead, and communication overhead. So having a larger staff than what's really necessary is always going to be much, much more expensive. So my point is that I actually think that these numbers, no matter how depressing they are, I do think that they're overly optimistic. I think the actual waste is significantly higher. But it doesn't stop there, because technical debt goes way beyond financial waste. And it turns out that if you look at recent research on security, you will see that there's a very strong correlation between security vulnerabilities and some major code smells, like brain classes, complex implementations, large classes, stuff that we're going to talk about in just a couple of minutes. So if we have a common problem in the industry, technical debt, that we know is causing a massive financial waste, it's impacting our security, then you would expect technical debt to be really, really, really high on any decision maker's agenda. Is that what's happening? Some of you are laughing. I think that's a pretty good answer. Because again, this is a well-studied topic. And if we turn our heads towards the research, we will see that the opposite is true. What's actually happening is that we developers were frequently forced to take on even more technical debt as companies keep trading, new features for technical quality. And I've been thinking about that for a long time. Why is that the case? Why we keep repeating these same mistakes decades after decades? And I like to think that the root cause lies in feedback. So let me take you on a short journey through the laws of software evolution. So how many of you are familiar with Lehman's laws of software evolution? Anyone heard about them before? So just a couple of you. So good, I got something new for you. I love that. So Lehman's laws of software evolution, I just want to focus on two laws here and see if they resonate with your experience. So the first law of software evolution is the law of continuing change. So this law says that our system is never done. We always have to adapt it, evolve it to keep it relevant, right? So we might have to respond to user needs, we might have to respond to competitors, we might want to enter a new market or whatever, right? So the law of continuous change, that's the reason why our backlog never gets empty, right? Because the only stable projects are dead projects. What I want you to do now is to notice that there is some kind of tension, some kind of conflict to the second law of software evolution, and that is the law of increasing complexity. And this law claims that when our software evolves, its complexity will increase unless we actively try to reduce it. Have you ever seen that happen? Yeah. And what's so interesting is this tension between them, because when the complexity increases, it becomes harder and more expensive to respond to change. So it's like a vicious circle. And the main problem I see with this circle is that if we look at the feedback timing here, those feedback loops are very different. When we add a new feature and put it into production, the moment we do that, we get a quick reward, right? We get a happy user on the other side, or maybe a less angry customer at least, right? Or we might win a new contract. We get all these good things, and it's an immediate feedback loop. However, the feedback from increasing complexity is pretty slow. In fact, I would like to claim that technical debt means a slow death, right? And once we notice the symptoms, it might already be too late. So this difference in feedback timing that you see here, it's like an open invitation to a decision-making bias that we psychologists know as hyperbolic discounting. So by show of hands, how many of you are familiar with hyperbolic discounting? One person. Okay, good. It's going to be significantly more people in a couple of minutes. Because hyperbolic discounting is very interesting, because it's a decision-making bias, and it simply means that we humans, we might make choices today that our future selves are going to regret. So to give you a very context-specific example, let's say that you go to a conference party tonight. And late in the evening, you decide to have that extra drink, despite knowing that you have an important business meeting in the morning. That's hyperbolic discounting, right? Hyperbolic discounting within psychology, it's frequently used to explain the psychology of addictions. It's also, coincidentally, the best description I have found on why companies make such a poor job at managing technical debt. Because just like the addict, we keep trading our future, in this case a healthy, maintainable and sustainable code base, for the lure of the next quick fix, a new feature. So, in the words of Mel Conway, somehow in software, there's never enough time to do something right, but there's always enough time to do it over and over and over again. So, how can we fight hyperbolic discounting in software? I think the main challenge we have in front of us is that code is a very abstract thing, right? Code lacks visibility. And that simply means we cannot really take a piece of code. We cannot take a large software system and pull it up and turn it around, inspect it for flaws or technical debt, right? We lack that level of visibility. And that makes it extremely hard to communicate between people like us who write software and people that might not know how to read or write source code, right? We have a communication chasm that we need to bridge. And I think it's our responsibility as engineers to help out bridging that communication. So how can we do that? How can we visualize something as technical as code? Well, before we can even visualize something, we need to know what to visualize. How can we measure something like code quality or even code complexity? Is there even such a thing? And I have to admit, I personally strongly dislike the word code quality. And the reason I dislike it is because it kind of suggests an absolute, whereas reality is way more complicated. And I've taken a lot of inspiration from the following piece of research. It's a paper from measurement theory. It's a pretty old paper, but I still recommend it because it hasn't lost any relevance over the decades. And what this paper tells us is basically that when it comes to things like code quality, then we are doomed if we look for a single magical metric to capture a multifaceted concept like code quality. There is no such thing. So what I've done instead is that I've taken a lot of inspiration from the second paragraph that you see here, that instead of looking for that magical metric, a much more promising approach is to identify various and specific attributes of code complexity, measure these separately, and then try to weight them together. So this is something I've been working on for the past 5 or 6 years, and I call the concept code health. Because I simply think it makes for a better discussion, right? It's much less of a judgment call if you say that the code is unhealthy. That means we can make it healthy, right? Rather than kind of, hey, it's poor quality. That's a judgment call. So I think there is some difference. Anyway, I just want to walk you through how the code health metric works so you know what you see when we get to the visualizations. So code health is a file level metric. So what we do here is that we take a file, we parse it into an abstract representation that we can then analyze for various code smells, these specific attributes of complexity. And these code smells that come in 3 different categories. At the highest level, we look for module level design issues. And just to give you some examples, let's start with low cohesion. How many of you are familiar with low cohesion, what it means, the term? So it's like 2/3 of the audience, good. So if I sum it up, I would say that low cohesion to me in this context means a module that has too many responsibilities. We have stuffed too many responsibilities into the same piece of code. And the problem with that is that the code becomes so much harder to understand because now I need to understand multiple business and domain concepts just to understand that piece of code. Another problem is that when we stuff multiple responsibilities into a module, there's also always the risk for things like unexpected feature interactions, which frankly are some of the worst bugs we can ever have. Now, even if you have a severe code smell like low cohesion, that doesn't mean we cannot make things worse, right? We can always turn it into a brain class. So brain classes are also known as gut classes, right? So that's when you have a class that's not only low on cohesion, it's also a very large class, and it contains at least one brain method. And brain methods are function level smells. So brain methods, you might know them as gut functions too. And a gut function is simply this large function. They're always large. It contains some really complicated logic, right? So lots of ifs and elses. And it also tends to centralize the behavior of the class so that each time you want to modify something in that area, you end up in the brain method. And over time, it becomes more and more complicated. Ever seen something like that? Yeah, I think you have. Now, then of course you also have classics like copy-pasted code, right? Dry violations. And at the lowest level of detail, I tend to look for various complexity smells. And one I really want to highlight is deep nested logic. So deep nested logic, that simply means that you have if statements, inside if statements, inside if statements, and then a while loop for good measure, right? And the problem with that type of coding construct is that there is some pretty strong research done on large systems that suggests that roughly 20% of all programming mistakes are due to things like deep nested logic. So once we know about it, we can start to avoid these anti-patterns. Now anyway, we measure all these things and a couple of others, and what we do then is that we can then aggregate the various findings. What type of code smells did we find? We can aggregate them, and we can categorize the results so that we can categorize each piece of code as being either green, which means healthy code that's easy to understand if we are programmers and have the required domain knowledge, or yellow, which is the part where we have started to take on technical debt, and unless we are careful, a code might degrade into the third category, which is unhealthy code. And unhealthy code is code that's extremely expensive to maintain, really hard to understand. So with that covered, we can now finally start to visualize code quality in a system. So let's have a look at the real-world code base. So what you see on screen now is a visualization of Ethereum, which is an open source decentralized blockchain implementation. And Ethereum comes in roughly 50 different Git repositories. So I want to walk you through this visualization so that you know what you see. Because what we see on screen here is a lot of code. What you see on screen is roughly 600,000 lines of code. Now, the way you read this visualization, it's called an enclosure visualization, by the way. The way you read it is that if you look at these circles, the ones I'm hovering over right now, then you see that each one of those circles represents the code in a specific Git repo. And if this was a monorepo, then those circles would simply be top-level folders in the repository. It's also an interactive visualization, meaning I can click and zoom in on any area of interest. And once I get to the lowest level of detail, I will see that each file with source code is visualized as a circle. And you see that those circles, they have different size. And size simply reflects the number of lines of code, so we know how big the potential problem is, right? The interesting thing is the color, which reflects the code health. So in this case, we see that we have one large red module, highly problematic code, and two green modules, which we expect to be much, much easier to work with. In general, I'm a big fan of visualizations because visualizations, they kind of tap into one of the most powerful pattern detectors that we have in the known universe, the human brain. And by visualizing things, we can suddenly start to understand a large code base. So I want to show you a couple examples. So here are two other systems. And let's start with the one to the left. The code base to the left, that's a code health visualization of React, a JavaScript library from Facebook. So how many of you are using React today? Wow. That's almost like a majority. So it's an extremely popular UI library. If we reason about it from a code health perspective, we see that most of the code seems to be either green or yellow. But in the highlighted circle, something called the React reconciler, that's like a subsystem, there is this band of red code. And I haven't shown you yet what that means to a business, but we already know that, code that's hard to understand, that doesn't sound like a really good thing to have, right? So if this was my code base, this is really, really important information to me because it's going to constrain what I can do with the React reconciler going forward. However, what we can do once we can visualize code is also that we can start to compare and contrast different code bases to each other. So let's contrast React to what we see on your right, the core CLR. So core CLR is the .NET Common Language Runtime from Microsoft. And it's a massive code base. So what you see here on screen is 8 million lines of code. So that's a lot of code. So what does it look like from a code health perspective? When we see this like this cluster of red code, right? I don't know, it almost looks like a Petri dish gone mad or something, right? Like a bacteria culture. But it's not. It's simply a lot of unhealthy code. And the question is, of course, not clear. What do I do with this? If I have like a million lines of red code, what do I do with this? How do I ever recover? And this is something I like to return to towards the end of this session. Before we go there, I would like to deliver on my promise and actually talk about how we can quantify the business impact of unhealthy code like we just saw. And I think this is important because I've been working as a software developer for almost 3 decades now. And during my career, I heard so many people tell me that code quality is important. Everyone seems to say that, right? Even managers. But yet, the moment a deadline starts to loom, then the first thing that gets thrown out of the window, that's the code quality, right? So somehow we pay lip service to it. And I think that if we want to change it and really, really turn code quality into the business concern it has to be, then we have to be able to quantify the benefits of having healthy code. Because only so can we move from knowing that code health is important to actually know about it. So with that in mind, 1.5 years ago, me and a colleague, Mr. Marcus Borg, we set out to study this empirically. So what we did was that we collected data from 39 different companies. Each one of them have multiple code bases developed by different people. So we collected many, many million lines of code. And what we did was that we had each piece of code categorized in the 3 code health categories, right? What we also did was that we also collected data on time in development. How long does it take to implement a task depending on if the code is green, yellow, or red? And finally, we also looked at how many defects have been reported in each piece of code, and we could then correlate that to the code health category. One important thing to mention about the data set is that we made sure to include companies from various and diverse industries. So we have everything from data analytics, retailing, healthcare, everything because we want to make sure that what we find isn't specific to an industry, like let's say automobile. We want to make sure that the findings actually generalize. And for the very same reason, we also made sure to include code written in 14 different programming languages because we want to make sure it's general findings. So we had code written in C#, Java, C++, Python, JavaScript, all the usual suspects. And everything I'm going to tell you is peer-reviewed. It was published at the International Conference on Tech Debt last year. And all findings are statistically significant, meaning it's not just a fluke. This is the way it's most likely is. Now, before I show you the actual data, I want to make sure that we all understand what we're looking at. So I want to talk a little bit about this, time and development. How can we measure such a thing? So one thing we wanted to avoid when doing this study was that we wanted to avoid put an administrative burden on developers, right? We didn't want developers to be able to, have to report that, okay, time spent in Jira or whatever, right? It's never going to work and everyone would hate us, right? So 2 negatives. So what we decided to do instead was to automate that process, and we designed the following algorithm for that purpose. So what we did now was that when you, as a developer, pick a card in Jira and move it to an in-progress state, that's where we start the clock. Then at some point, you make a commit, and that commit references that Jira task, right? That's where we know that, okay, this task is done now, the code is written for it. And if the task is really done, then the time in development is the time from moving to in progress until the commit. Simple enough. Except that most tasks are way more complicated, of course, right? So if you do multiple commits and touch multiple files, then we made sure to kind of calculate the time between commits. And then we simply sum it up at the file level. So by doing so, we now had a data set where we had many thousands of files, each with a known code health and each with a known time in development for any task that touched that file. And since we had access to Jira, we could also look, okay, this commit, was it a bug fix or a new feature, right? So we also knew the defect density. And that made it possible to finally answer this question. Does code quality actually matter to a business? And a quick spoiler is, yes, it does. Otherwise, it would be a really short talk. So let's look at the actual findings. The first thing that we found was pretty interesting. We found out that implementing a task, fixing a bug, doing a new feature, whatever, is more than twice as quick in green code as compared to red code on average. So let this sink in for a moment. Is this important to a business? Well, it is, I like to say, because this is basically speed to market. So let's say that our company, we have a code base that's red. That means that if we need 2.5 months to implement a certain capability, then our competitors with green code can have the same thing in less than a month. It's going to be impossible for us to keep up, right? Now, I have to admit that this first finding, it didn't really surprise me. This is pretty much what I would have guessed based on my experience. What did surprise me, however, was the next thing we looked at. Because what we did now was that we realized that averages can be a little bit misleading. So what we wanted to do instead was that we wanted to look at what's the variability depending on code health category. Right? So instead, we looked at what's the longest maximum time it takes to implement something, depending on which code health you have. And what we found here is quite dramatic. It turns out that for green code, the maximum time you will need is very close to the average. And to me, my interpretation is that this simply means that green code is predictable. It takes roughly the same time each time I touch it. Whereas, as you can see for red code, all bets are off. The maximum time can actually be an order of magnitude longer compared to green code. So what would this mean to a business? It would mean uncertainty. And let me guarantee you, in software, no one likes uncertainty. And I can only speak from experience. I mean, I'm currently working as a CTO. And as part of when you're a CTO, one of the things you do all the time is you make promises to people, right? So I might promise my sales team that, yeah, with this absolutely great capability, right, we're going to have it out in a month's time. If our code would have been red, I could never ever make such a promise because it could as well take 9 or 10 months, and I would have a lot of disappointed people on the other side, right? If I instead take on my developer hat because I do love to write code, then I also dislike uncertainty because uncertainty is what gets me into stress, what gets me into tight deadlines, what forces me to do overtime, right? So no one likes uncertainty, and red code comes with a lot of uncertainty. Now finally, the last thing we looked at was the defect density. Is there a difference between healthy and unhealthy code? And it turns out there's a massive difference. In fact, red code has on average 15 times more defects than green code. Again, do you think this matters to business? What's the problem with defects? Well, I see two problems with them. The first is that if you have red code and deliver 15 times more defects, then it's going to impact the product maturity experience of your customers, right? But what might be, and that's a problem in itself, but what makes it worse is that, defects have this property that just like in the old Stephen King movies, they come back. And they come back in the shape of unplanned work. And unplanned work, in the words of Jin Kim, is the silent killer of IT projects. And I've seen companies that spend 60 to 70% of their work week on unplanned work. It's a real productivity killer, constant context switches, impossible to predict when anything would be delivered, right? It's very demoralizing to work on unplanned work rather than doing the next cool innovation. So with that covered, I'd like to take a step back from the business and talk a little bit about the programmer perspective. How does these findings, how do they impact us as programmers? Because after all, you could make this case that technical debt, if it means that we waste 42% of our time, you know that there's already a global shortage of software developers, right? And if we waste 42% of our time, that simply means we become even more in demand, right? Maybe that's something we can use to negotiate our salaries. So maybe technical debt is the developer's best friend. You seem a little bit skeptical. And that's right. That's very good. Because no one likes technical debt. No one loves to work with bad code. And the reason I can say that with confidence is because I read this really, really good book a couple of months ago. It's called Rethinking Productivity in Software Engineering. And last time I checked, it was actually free on Kindle. So it's a collection of research papers. It's pretty exciting. I highly recommend it. And there's one paper in particular that I really enjoyed. It's a paper that studied developer happiness. Because it turns out happy developers are productive developers. I mean, who knew, right? And what's really interesting about that paper is that they look for reasons for making developers unhappy. And the top 3 reasons all relate to code. So let me show you what those 3 reasons are. And let's see how they relate to the findings I just showed you. The number 1 reason for unhappiness amongst developers, according to the study, is being stuck in problem solving. It's something we strongly dislike. And given what I just told you about the unpredictability of red code, it's very easy to see how we can adapt there. So let's pretend that we work for the same company and we attend our daily stand-up. And during that daily stand-up, someone comes in and say, hey, you know what? We have this crash in production. We really, really need to attend to it. You volunteer because, after all, you're vaguely familiar with that area, so you think you can fix it quickly. So you start to look at the code, you start to debug it, and at some point, you end up in red code. And now we know that all bets are off. So what you thought would be a simple fix in 2 hours ends up taking 10 days. And being stuck in problem solving, it's very easy to see how that leads to the time pressure. Because now, not only is it extremely stressful for you as an individual, because you kind of feel that, okay, I'm not really delivering what I promised, it's also going to put a lot of stress on the organization, right? Because remember, we have a crash in production, right? I like to think that this combination is the main reason why we developers dislike to work with bad code. And there is this absolutely wonderful quote in the paper that we developers, we suffer tremendously when we meet bad code that could have been avoided in the first place. So with that covered, how can we use this data if we have it? How can we use this knowledge of how code health and code quality correlate to a business impact? I would like to share a couple of use cases that I've seen work well in practice. The first one is, I think, really important because, as we have seen, code quality constraints our business. So one thing we can do by using visualizations like this is that we can make sure that everyone, not only engineering and developers, everyone, including product and management, have the same shared situational awareness of what the system looks like, where the strong parts are and then when the weak parts are. And this is something, once you have it, that you can use to fight hyperbolic discounting. Because it turns out, once you can prime decision makers to think about future risk, then you actually take away a lot of that bias. So one way of doing that is to take a map like that, and let's pretend we work on React. So if we are going to add a new feature, and we see in our roadmap that, yeah, we have 5 features planned for the React reconciler, and we see that a lot of that code is red, the rest of it is yellow, then we know that there's a massive risk that this is going to take so much longer and deliver more defects than we're comfortable with. So we can now either choose to accept that risk and simply plan additional time because we know we're going to need it, or even better, we can take a step back and use this as an opportunity to refactor the code so that we can deliver any future features in a safe way and a much more efficient way. And that's actually what I like personally, what I like the most about this data is that it makes it possible to finally make the business case for refactoring. Because refactoring can now come with a business expectation. Because I can actually say with confidence that if we have this red area of code and we manage to turn it green, then we can expect any future IDs and features that we have for that area to be delivered twice as quick on average, with a magnitude of order uncertainty reduction in our estimates and guesses, and a significant reduction of defects. Now, with the code quality part covered, I like to return to one of the problems I kind of skimmed over earlier, and that is how to prioritize improvements to large amounts of complicated code. So, do you remember this one, the core CLR, right? 8 million lines of code. And not only that, it's 8 million lines of C++, right? So that's pretty scary. Now, how do we approach this, right? So we have probably 2-3 million lines of red code here. And what would happen if we say that, okay, let's refactor all this red code and make it green? We would have to stop all feature development for like what, 3-4 years? And what would happen then? Well, we would be out of business. We would be Netscape. And we don't want that. So we always have to do this trade-off between new capabilities versus adding new complexity. Remember Lehman's laws, right? It's always a trade-off. So how can we find that trade-off? Well, one concept I've been working on is something I call behavioral code analysis. So behavioral code analysis, the whole idea here is that the code itself, if it's healthy or not, that's really important. That's like the foundation. But it might be even more important to understand how we, as people, the people organization, how we interact with the code we're building. So to pull off a behavioral code analysis, what we need to do is we need to have some behavioral data. And it turns out it's something we all already have. We're just not used to think about it that way. I'm talking about our version control system. Because our version control system, it's virtually a goldmine of behavioral information. Our behavioral data source, version control, one of the things I like the most about it is that it gives us a time dimension into our code. Using version control and Git data, we can actually see where did we work and how did that focus shift over time. And this is important because this is something we can use to finally prioritize technical depth based on impact. So let me show you how that works. So what you see here is a visualization of core CLR. It's the same visualization style as before with the circles. The difference now is the colors carry a different meaning. The colors no longer show you the code health. What they show you is the change frequency of the code. That is, how many commits have you done to the various parts of the code, right? And the more red something is, the more development activity. And this is important because development activity is never, ever evenly distributed it tends to cluster. And we can pretty much see that here, that even if we have 8 million lines of code, most of that code is stable. And in a technical debt term, stable code means code with low interest. So even if we have some code quality issues there, it's of course not ideal, but we can basically view it as a free loan, right? A zero interest loan. On the other hand, these red circles, the ones I call a hotspot, if we take on technical debt there, if we have poor code health in a hotspot, then that high change frequency, it's going to act like a really, really high interest. So this is like the technical debt equivalent of an SMS loan or something, right? It's going to be really expensive. So hotspots give us a way to prioritize a starting point for refactoring. But there's a bit more to it. We need to actually question ourselves here, or I need to question myself. Is this really an actionable insight that I'm delivering to you? Because if we look at this massive system, then you see that the number one hotspot right now, it's something called gentry.cpp. It's a single file with 14,000 lines of code. And it's 14,000 lines of C++ that looks like this. So do I have any volunteer to clean up that code? Who would like to refactor 14,000 lines of code that looks like that? Not so. How much time? Yeah, how much test coverage is simple to answer. It's absolutely zero. Other thing is, I have to admit that I'm making a lot of fun about C++, but I actually used to be a C++ developer myself. I did that for 10 years, and I know what you're all thinking. That's 10 years I never get back. And it's absolutely true. The thing is that I have a lot of respect for code that looks like this. I know that refactoring this piece of code is going to be a massive risk, right? And what's going to happen most likely is that we're going to branch out, we're going to work on it for a couple of months, and we're never, ever going to be able to merge it back, because in the meantime, our colleagues have been working on the code, right? So this is a losing battle. So what we need to do is to be much, much more specific in our recommendations. So for that purpose, I use another behavioral code analysis technique that I call X-ray, hotspots X-ray. So what I do here, when I come across these really, really complicated hotspots, what I do is I take them and I parse them into separate function blocks. And then I look at the Git log to see where do each commit hit over time, and I sum it up so that I get hotspots at the function level. Let's make this specific by looking at the X-ray of gentry.cpp. This is what it looks like. What we get out of X-ray is basically a prioritized list in which order should we start to pay down the technical debt here. And the number one hotspot at the function level is a function called GT clone expression. We can see that we have done 42 commits that touch that function just over the past year. It's like once a week, some developers impacted by that code. We also see, if we look at the last column, it says cyclomatic complexity. So who of you are familiar with cyclomatic complexity? So that's like most of you, good. So you know it's basically like a measure of how many branches do you have in each function, right? Each if statement, each loop, plus one, and so on. What's a good threshold for cyclomatic complexity on general? How much? 12. That's typically what I've seen as well. The threshold for where it's considered to be very, very high complexity is there at 12 or 15 maybe. Here we have 112. I have to admit that cyclomatic complexity is not a particularly good metric. It's actually a pretty poor complexity metric. But it's really not a complexity metric originally. It's actually a testability metric. And that's why I use it here, because cyclomatic complexity is very good at one thing. It's very good at estimating the minimum number of unit tests I need to cover just that function. And I would need 112 of them. That sure says something about how complex it is. We also see that the function consists of more than 500 lines of code. That's a lot for a single function, isn't it? It is. But 500 lines of code, it's much less than 14,000 lines of code, which was size of a total hotspot. And 500 lines of code is definitely less than 8 million lines of code, which was total system. So more importantly, we are now at the level where we can start to act upon this data and its actions and refactorings we can then do that are going to be based on how we, as an organization, work with the code. So to sum it up, to me, hotspots send a positive message, because hotspots basically tell me that, no, I don't have to fix all my technical debt. And what you see here on screen is one of the most important graphs I want to show you today. what you see here is on the x-axis, you see each file in the system, and those files are sorted according to the change frequency. That is how many commits have you done to each file, and that's what you see on the y-axis. Now, this is nothing specific to core CLR. This type of power law curve that you see here, that's something I've seen in every single system that I've ever analyzed, and I probably have analyzed like 300-400 code bases by now. So this seems to be the way software evolves. And it's good for us, because this is why we can make technical debt payments that actually carry a meaning and impact. Because as we see here, most code is going to be in the long tail, the low interest part, whereas most of our development efforts is in a very small part of the code base. And that's the part of the code base where we really, really want to make sure that we keep the code as healthy as possible. So what I want to show you today is that we can actually address technical debt with a data-driven approach. And to do so, we need two different dimensions that we need to piece together. One of them is the quality dimension. We basically need to separate the good from the bad. But if we find that we have a lot of red and yellow code, a lot of unhealthy code, then we also need to prioritize those findings so we can start to act on them and address them. And the way we would do that is by using the hotspots. Now, the last thing I want to talk about is that during all my years in the software industry, I had so many people that have been telling me, no, we don't have time to refactor. No, we don't have time to automate tests. No, we don't have time to fix our architecture. And it's almost like there is this perception that there's an inevitable trade-off between speed and quality. But what we find here in the data is the opposite. We actually find that if you want to have high quality, then you also need to be able to move fast. There is no trade-off. In fact, the opposite is true, right? Healthy code is code where you can not only deliver quickly, but you can also deliver with significantly fewer defects than unhealthy code. And with that covered, I would like to give you a couple of references if we want to look deeper on this data, and then I'll be happy to take questions. If you're interested in reading the paper, the first link here, that's like a quick summary that just focuses on the results and benefits. The second paper is the formal research paper, right? So that's the one you read if you want to know, okay, what type of biases did they control for? How did it make the data collection? What type of analysis did they run? Stuff like that. The tool we use for the studies is the CodeScene tool that we used for the visualizations and data collections. And if you would like to try this out on your own code, then there is a new free Visual Studio Code extension where you can kind of get real-time code health feedback. So if you enjoy this, please check it out and consider to support it. Finally, I'm really proud to announce that in just a couple of weeks, I will release a second edition of Your Code's Crime Scene. So in case you're interested in reading up more about hotspots and behavioral code analysis, that might be a good starting point. For now, I really just want to thank all of you for showing up to this presentation, and may the code be with you. Thank you. Thanks a lot. Yeah, let's see a couple of questions. Yes, please.
Yes. Since there is one thing we're going to conclude from the study of business impact of predictability is that people knowing about technical debt don't make it to action.
Yeah.
What do you think about this issue?
So I think one of the main reasons that people aren't really acting upon this is because we as developers, we suffer all these consequences. And I think we have a really hard time to communicate around something as technical as code. We speak a completely different language than the business. And I also think that the business, even if most business managers I know about, they know that technical debt is important. The thing is that it's very easy to kind of, you might have that feeling in your stomach, and it's very easy to kind of ignore it because you don't know how is technical debt impacting us? Where is it happening? How big is the waste? So I think if we really want to address this, what we need to do is we need to bring visibility to it. If I as a business manager could see that, okay, I actually have a 30% waste and it's happening in this area of the code, and then I would know that this is an important area because we are going to expand to this particular market and we need to do something here. Then suddenly it becomes an urgent problem. So I think we need to bridge that communication gap. That would be my response. Yes, please.
What if your teammates also don't want to solve their technical dates?
If your teammates don't want to solve your technical debt,
exactly.
change teammates. No,
what
on,
if you
on a
don't?
more serious note, it's a challenge. I don't think developers in general, we don't like bad code, right? But what I think it's also an experience question, because I know that if I look back at the code I wrote 10 years ago or 5 years ago, I'm not particularly proud of it. And I like to think it's a good thing because we're evolving. So I think it's about helping people gain that knowledge. And what I think we can do, one of the techniques I've seen work really well is to do team activities like mob cleaning, right? So I know Ivan Houston has a really good write-up on that. You simply get the team together. And to make it work, I would set a fixed cadence, like say each Tuesday at 1 o'clock, we spend an hour cleaning up some code, right? Because then we have the opportunity to kind of learn from each other. And even better, once we've cleaned up the code, everyone on the team has this before and after comparison that they can do. And I think that's the way how we kind of sell the value of healthy code to our teammates. So I hope that made sense. Perfect, thank you. And I see that I'm out of time. I'll be hanging around. Am I out of time? I'm out of time. But I'll be hanging around. I'll be happy to continue to discuss this. Thank you very much.